morning, everyone. It's great to be here today with such a great audience. I'm excited today to share some of my work on scalable multi-agent motion planning in mixed environments, and in particular, focusing on two key challenges, one on how we reason about dynamics in a scalable way, and also how do we, when we go to these uncontrolled, decentralized environments, and we have multimodal uncertainty, how do we come up with efficient decision-making algorithms that are also not overly conservative and safe? So the outline for the talk today, I'll start with a brief introduction on some of the key challenges with respect to these two areas in multi-agent motion planning. And then the first key part of the talk will be over scalable multi-agent motion planning with dynamics, which is part of the work that's been accepted to ICRA 24. And then I'll also talk about some of my current work on scalable multi-agent motion planning, but in presence of uncertain and uncontrolled multimodal agents that have a lot of practical relevance in many real-world applications. So I think a lot of speakers prior to this talk motivated this problem. Multi-agent systems are everywhere now, and they're continuing to expand into new use cases every year. The first sort of a large-scale deployment of such systems were in Amazon fulfillment centers, where we had hundreds of thousands of these robots deployed. These have been very effective, very efficient, but they often follow very rigid execution schedules in a very controlled environment. And so recently we've had multi-agent systems in port operations where the vehicles have non-trivial dynamics and they're operating in a bit of a less controlled environment. Sometimes there may be humans or other vehicles that are teleoperated or just other autonomous systems that are not directly coordinated in these environments. And then we've also had this surge in robotics companies deploying these robots in sidewalk delivery applications where the number of these robots is increasing day by day. We have the additional challenge of the environment uncertainty. We may have variable friction, different types of weather conditions. And as the number of these robots increases, we also have the challenge of coordination among the robots from the same provider or from different providers that will become relevant. And then finally, we also have these robots share this environment with humans as well, sometimes crowds, numbers of people walking around. And then finally, autonomous driving has been a long-lasting challenge for the robotics community and the multi-agent community. And here, the big problems come often from the interaction between agents and also being able to understand their level of cooperativeness and make decisions safely, but also efficiently. So with all of these problems, there are lots of ways to categorize the key challenges. The first axis that I'd like to talk about is scalability, which many of the people in the community have looked at. And in particular here, the biggest problems come from the exploding number of states as we have to reason over the joint state space of many agents, and also number of constraints as the number of interactions among those agents increases. The problems are often large, but in many practical scenarios, they're sparse, meaning that not every robot necessarily have to interact with every other robot at every time step. So there are some nice structures to this problem that can be leveraged. And the biggest challenge is sort of transitioning this scalability results from simulation into the real world and actually ensure that the executions are reliable. And so making sure that we have efficient and safe execution under realistic conditions is a big challenge. We've had a lot of advancements on the scalability axis. It's much harder to transfer those into the real world. And in addition, we have domain-specific rules and regulations. Each application area has its own set of social norms, rules and regulations that these decision-making algorithms have to abide by. And then finally, as we exit this sort of controlled warehouse environments into more unstructured areas, we have this inter-agent influence and interaction where our actions have an impact on how the other agents react to us and vice versa. We also have multimodal uncertainty, meaning that oftentimes we have multiple hypotheses about how the world might evolve with agents that we may not know their intents exactly, and partial observability. When we interact with agents in realistic settings, it's very likely that not all agents are going to have the full knowledge of the world, which is where a lot of sort of game theoretic methods come in. So in the first part of the talk, I want to focus on this intersection between scalability and execution reliability. In particular, how do we bring dynamics more into these multi-agent planning algorithms in a scalable and efficient way? So going over a bit more detail of the existing approaches in this space, the first category of solutions are the multi-agent pathfinding algorithms. There is lots of papers on these in different variations. They call them MAPF algorithms. One notable example is the conflict-based search method that there's been, it's a very highly cited paper. There's lots of different variations. And this is a very scalable, this family of solutions are very scalable. And for hundreds of robots now, we can get plans in order of sub-second or a few seconds. However, this comes at a cost of executability because these methods often make very restrictive simplifying assumptions about the robot dynamics by discretizing states and action spaces. And also, they require a very rigid execution schedule to actually make them work in practice. So oftentimes they're not really transferable to real world unless we can enforce those rigid structures in the environment and in the robot itself. The second category of solutions, the multi-agent motion planning algorithm, or MAMP, these try and kind of reason about the dynamic constraints of the robot over the full horizon. And so they have that executability aspect to them because the motions are generated in a realistic way, consistent with the physics of the robot. But they're not that scalable because of this. And oftentimes, whether it's trajectory optimization-based or sampling-based method like the kinodynamic RT planner here, they come up with poor solution qualities for many robots. And the solve times are in the order of tens of seconds for a large team of robots. So this brings us to our question: how do we design a multi-robot motion planning algorithm that's scalable, executable, and adapts to online changes? And so the solution that we propose to this problem is a new algorithm called conflict-based model predictive control, which is inspired from some of the tools in the MAPF community and also model predictive control as a low-level planner. So on the right, you can see sort of the demonstration of how this algorithm generates realizable motion plans for 12 robots interacting with each other and swapping locations. And the key aspects here are that we're reasoning about dynamics using MPC at the low level. And at the high level, we use this conflict resolution tree to be able to efficiently reason about inter-agent conflicts. So the key insight that makes this happen is that at the high level, we have this conflict tree that allows us to incrementally reason about these constraints and add them while leveraging the previous feasible solution as much as possible. And so we're basically decomposing this large optimization problem into a sequence of smaller problems by incrementally adding constraints. And that means that each subsequent solve is very similar to the previous solution with one more constraint. And so that sort of intelligent warm starting allows us to get very good scalability while satisfying the dynamic constraints on the robot. And so I'll go through sort of a simple example of how this works. So let's say we have a 3-robot example in this case, where each robot has its own MPC instance. On the right side, we have the conflict tree, which at the beginning is empty because there are no inter-robot conflicts. And then in the first iteration, each robot in parallel solves its MPC problem with respect to its own constraints. And so here, there are no collision avoidance constraints. And if the solution is collision-free naturally, we'll just return and execute. Now, after collision checking, if we find collisions between pairs of robots, in this case, let's say robot 1 and 2 collide at time t1. For each conflict between robots, we define 2 constraints, one on each robot. And so each node basically says either robot 1 has to avoid robot 2 for these set of time ranges, or robot 2 has to avoid robot 1 for that same time range. And the key here is that as opposed to just constraining a single location time pair, we're constraining a location time range. And so this is important because in continuous time in receding horizon fashion, if you only constrain a single location time pair, you're likely shifting the collision forward in time and thus resolving a lot of repetitive solves that are very similar. But this kind of location time range constraint definition allows us to have a single constraint pair for each pair of robots. And then each node also has a cost, in this case, a cost to go. Could be a distance heuristic. If you have a heterogeneous fleet, it could be a velocity or acceleration dependent term that captures different dynamic capabilities of the robots. And so at the next iteration, we pop the lowest cost node, in this case, the node on the right, and we resolve that optimization problem with this updated conflict that we added. And so the key here is that we're still utilizing the feasible parent solution for this new solve. And that's where a lot of the scalability comes in, where each subsequent solve ends up being much faster. And so we repeat the same process until we get a conflict-free plan. So here's some of the results of the algorithm comparing with prioritized MPC or distributed MPC. Prioritized MPC is where we assign a random priority to each robot, and the lower priority robots have to avoid constraints on the higher priority robots. And distributed MPC is basically solving all parallel MPC problems where each robot is constraining itself against the predicted trajectory of the other robots. So you can see that CB-MPC is able to go through this very tight navigation scenario where there are two obstacles and accomplish this motion. Prioritized MPC becomes infeasible because of the excessive number of constraints added on lower priority robots. And distributed MPC is similar to CB-MPC, except that it doesn't have the high-level collision resolution and coordination mechanism. And in these type of sort of symmetric cases with head-to-head collisions, this coordination becomes really important in terms of feasibility and actually achieving the goal state. So we also executed these solutions on hardware on these Capera differential drive robots in mocap. And so you can see that a similar type of limitations exist with distributed MPC and prioritized MPC, whereas in the conflict-based MPC, our proposed method, the robots are able to seamlessly navigate around each other. And this interesting behavior at the end where one robot makes way for the other. So this kind of takes some of those MapF tools that have been very effective and efficient at resolving collisions fast and merges it with model predictive control to be able to negotiate these type of tight interactions between robots in a physically realizable way. And here's the open environment results that I showed earlier. And on the right, we have a table of the results summary. The important things is the average computation time per robot. The absolute value on these doesn't matter because you can do linearizations and convexification of the cost functions and bring those down. But it's the sort of relative scaling that CB-MPC is multiple times better than prioritized MPC, and it's the only instance that's able to solve the 12 robot problem at the end. And part of the scalability comes from this C average metric, which is the average number of constraints added per each optimization solve. And you can see that CB-MPC has significantly lower average number of constraints added per each iteration. And when you combine that by utilizing the previous solution as much as possible for the child node solves, that's where sort of the scalability comes in. And so this is the results of the open environment for the 4-robot case executed on hardware. This is the distributed MPC, kind of resulting in the same type of deadlock where you can see robots don't coordinate, so they both are constraining themselves against the same type of constraints. Prioritized MPC results in an infeasibility because of the excessive number of non-convex collision constraints. And CB-MPC is able to successfully coordinate the robots to their goal states. And finally, this is a sort of a more realistic real-world example where you have randomized start-goal locations and a randomized map, which can look like a realistic warehouse. On the right side, we're showing success rate. Okay. Delayed a little bit. On the right side, you can see the success rate. The x-axis is the number of robots. And we're comparing CB-MPC with prioritized MPC and distributed MPC across different number of robots. And so you can see that as the number of robots increases, the need for coordination between the robots and this sort of collision resolution collaboratively becomes important. So distributed MPC is able to maintain similar performance for lower number of robots, but as the number of robots increases, CB-MPC outperforms. And this trend will continue as you add more robots. The next result is looking at the average computation time per robot. And so you can see that the scalability is clearly demonstrated here, where as you add more robots, the other algorithms both have worse absolute solve time, but also they scale worse. And so this kind of collaborative conflict resolution allows for much better scalability with increase in the number of robots in this environment. So The key takeaway from this part was that we took a large, tightly constrained optimization problem, and solved in parallel problems when they were possible, and when there were conflicts, we used this high-level conflict tree in continuous time to resolve these collisions efficiently. However, when we go to decentralized real-world environments, we're dealing with agents where we don't necessarily know their true intent. And oftentimes we have multiple hypotheses over what their intents might be. And so this comes up all the time in autonomous driving or sidewalk delivery applications, where we can't exactly determine what the agent's going to do, but we have multiple hypotheses about what might happen in the future. So this part will focus more on how do we deal with this in a more efficient and non-conservative way. And so in particular, what we mean by multimodalities, in this example, let's say we have a robot and a pedestrian trying to navigate around in a sidewalk. The pedestrian may choose to go to the right side, where the robot has to react and go to the other side to avoid the collision. It might also choose to go to a different side, where we have to adapt accordingly. So our control action has to be a function of the possible realizations of the pedestrian mode. And you might ask, what happens if we constrain ourselves against both of these possibilities? If we do that, then we come up with a very conservative plan where a single input sequence has to satisfy multiple set of constraints. And you can see this quickly runs into infeasibilities as we add more agents, and each agent having their own set of multiple predictions. And so that's kind of why traditional motion planning methods that only generate a single input sequence won't really be efficient in this case. Fortunately, we have contingency planning as an approach that allows us to capture this mode feedback and say that, okay, at some point in the near future, we will have a realized mode. And so we can be conservative for the part of our prediction horizon, but then after that, we can assume that one of these modes will be realized. And so this will allow us to be a lot less conservative and remain feasible for harder problems. However, there's this question of, we have discrete mode uncertainty. We don't know whether the pedestrian is going to go left or right, but we also have continuous state uncertainty. So even if we know the mode of the pedestrian, there is still uncertainty about position, velocity, from whatever perception input that we're getting. And so the question is, how do we parameterize our control policy to simultaneously capture both of these types of uncertainty and remain both safe and also efficient in these challenging navigation scenarios around humans or other uncontrolled agents? And so to solve this, we draw inspiration from something called the disturbance feedback policy parametrization in control theory. I won't get into too much math, but just enough to convey the idea. So traditionally, we have our AX plus BU dynamics equation that dictates our straight state propagation. And we also have some disturbance on our dynamics denoted by W here. And so every time we have a measured state xi, the difference between that and the predicted state from our dynamics would be the disturbance at the previous time step. So that's kind of very traditional control theory. And so disturbance feedback parametrization says that we can write our control policy U as an affine combination of H and K, which is our control parameters, times this feedback Wi. And so the reason for this particular choice is that if we actually substitute equation 2 and 3 into our dynamics, the prediction in the states xi plus 1 becomes affine and convex in H and K. And so this control formulation allows us to be able to utilize our efficient numerical tools and standard fast solvers to actually solve this problem. However, this is all egocentric. So this is disturbance on the ego agent. But we can actually flip the problem and think that the uncertainty could come from another agent, from the uncertainty in the other agent observation. So it's still a disturbance on our system that we have to compensate with our control policy, but it's just not from the ego agent, it's from another agent. And so if we take that approach, we can rewrite this control parametrization as this combination of H and K, where our H is just nominal feed-forward control, and this K is observation feedback over the agent. And instead of having that term Wi, which was our disturbance over our dynamics, we have this O minus expectation of O, where O is the state of the obstacle. So this O minus expectation of O is basically describing our observation uncertainty. So with this parametrization, we took our original disturbance feedback parameterization and said that the uncertainty could come from observation in the other agent. And so I'll show how this can be combined in contingency planning framework to allow better feasibility. So let's get a visual intuition for this. Traditionally, in contingency planning, we have something called the robust horizon, where up until that robust horizon, all of the constraints have to be satisfied because we don't know what the agent might do. But we know at the near future, one of the possibilities will be realized. And so the superscript U1 and U2 describe our control action, assuming that we're in one of those modes. And so the biggest challenge here is that we also have these chance constraints that we have to satisfy along the horizon for each one of these modes. So we may have a different chance constraint for mode 1, another chance constraint for mode 2. Traditionally, we have to come up with a single input sequence that satisfies this chance constraint along each one of the modes. And with this disturbance feedback parameterization, this K gain allows us to have a richer policy representation along these modes, to have these sort of variations where for every uncertain realization of the obstacle, we'll have a unique input trajectory. So in this case, I'm using a superscript K1 for K corresponding to mode 1 and K2 likewise for mode 2. And so this magnitude of K basically describes how much spread we have in our trajectory or in our policy representation. So the larger K means more spread, which helps us compensate for higher uncertainty. And the smaller K means smaller sort of uncertainty levels. And we can have a K for every time step in the prediction horizon. I'm just abusing the notation here to convey the idea. And so the key takeaway here is that this K actually shapes the joint distribution of X, the ego agent, and O, the obstacle, which allows us to have a unique ego trajectory for every realization of the obstacle, instead of trying to satisfy all the obstacle uncertain possibilities with a single input sequence. And what that manifests itself in terms of performance is better feasibility, which means better navigation. As longer we can remain feasible while satisfying our safety constraints, the more efficient we can be in our navigation, because we can always be safe and just stop in place. And so the goal is to maximize our feasibility throughout in places where we have really challenging chance constraints to satisfy. So here's a very simple example that kind of conveys the idea. We have a pedestrian, a unimodal, multimodal pedestrian walking across the street. It can either go left or right with the red and green mode. And there's also observation uncertainty along each one of these modes. So this can come from the measurement that we're taking from the human, or it could be encoded naturally in the prediction model. And so before we interact with the pedestrian in figure A, the two hypotheses coincide. So we have a single trajectory. And as we approach the pedestrian, we maintain a single hypothesis for each one of the possibilities. So the red trajectory is clear with respect to the red mode, and the green trajectory with respect to the green mode. And for the green mode here, we're visualizing the policy parameterization that I explained earlier. And so you can see that it corresponds to, for every green realization of the obstacle or the pedestrian, we would have one of these smaller green trajectories in response. And so that's kind of showing how this policy parameterization actually looks like in practice. And you can see that in the bottom row, we're plotting the K feedback gain over the horizon for each one of the modes. And so the larger magnitude, which shows in the green, and in this case, we only have X feedback because the pedestrian moves mostly in one dimension. We could have multi-dimensional feedback depending on how the pedestrian moves. So the larger magnitude of K here corresponds to more spread in the trajectory. And so you can see, comparing figure B to figure C, we have in B, we have a much larger spread than in C, and that comes from the optimized feedback gain that helps us satisfy those chance constraints. We also show some comparisons here. Again, this is some ongoing work. Hopefully you'll see more extensive results on this when it's published. So there's multi-modal MPC, which reasons about both this discrete and continuous uncertainty, versus maximum likelihood MPC that only reasons about the most likely mode. And so it doesn't take into account both possibilities. The branch MPC is where we only reason about the discrete uncertainty. So there is no K parameterization, or there's no K feedback gain. We just have a branch policy. And robust MPC is where we only reason about continuous uncertainty, and we don't take into account the branching. So there's no branching, it's just a single input sequence. And so you can see that regardless of the mode realization of the pedestrian, reasoning about both discrete and continuous uncertainty allows us to have a much better navigation performance, where you can see that in both cases, the MMPC case reaches the goal on the other side faster than the other agent. The maximum likelihood case, if the pedestrian behaves as expected, it performs similarly. But if the pedestrian does something of the lower likelihood mode, it ends up behaving very unsafe in the second row top figure. And the branch MPC and robust MPC also become conservative relatively. So the key takeaway here is that reasoning about both discrete and continuous uncertainty with this type of feedback parameterization allows for much more efficient navigation and higher feasibility. So in conclusion, we talked about two key points in multi-agent systems today. One was the intersection of scalability and execution reliability. We introduced conflict-based model predictive control to bridge this gap. And this is not a replacement to the MAPF algorithms. We can still use our MAPF methods as the high-level heuristic to provide sort of discrete route planning and reduce the number of collision avoidance constraints. But that this kind of dynamic aware low-level controller allows us to do coordination while satisfying our constraints, our dynamic constraints. We also talked about this intersection of execution reliability and where we have environment that's hard to have a single hypothesis over, where we have multiple hypotheses, and introduce this policy parameterization to simultaneously reason about discrete and continuous uncertainty, and showed that that is relevant in practical cases and also important to reason about to be able to satisfy these chance constraints efficiently. I'd like to also thank my advisors, Professor Aaron Johnson and Lorenz Biegler, for their support, and all the collaborators for making this work possible. And with that, happy to take any questions. Thank you very much.
Thank you, Ardalan. Very nice presentation. We have time for questions.
Very impressive results. Wondering about in the first part of the talk, when you're deciding which regions are under collision, are these sent to some server and then back propagated, or this is locally done through communication?
Yeah, so I mean, the way in implementation, you can do two things. You can either have this sort of centralized server, as you said, where you centralize planning and centralized sort of execution, or you could have sort of a decentralized way, but with full communication along with the agents. So both in implementation are possible, but in this case that I showed, it's mostly done through the centralized server.
Yeah. All right, amazing talk, and the CB-MPC results were really cool. And so since I have you here, I'm going to ask, what are the weaknesses of this method? Where does CB-MPC struggle?
Yeah, so the biggest thing is completeness guarantee. With any local optimization, you always have that problem. You can never guarantee that this problem can be solved if there's a solution. And in this case, we're assuming deterministic intent of all agents in the first part of the talk. So I think there are some extensions where you do this collision checking probabilistically, and sort of it would be interesting where you have this tree over hypotheses instead of this deterministic sense that we have. So I would say these are the two key points. And then another limitation is that I think there's a lot more work to be done. This is kind of a local planner. Integrating it with a global planner while still satisfying feasibility is also a big issue, because the global planners are often over just the position trajectory, whereas a local planner plans over the full dynamic space. So sometimes the global planner says do something, but the local planner can't actually accomplish it. So it's unclear in those cases, how do we fill the gap? And so local planner only knows about velocities and positions, but global planner only knows about positions. So I think there's a lot of interesting open areas there that this work needs to be better at.
Great job, thank you.
Yeah, yeah.
So, I saw a little bit of the presentation, sorry for that, but I saw the point about talking about discrete and continuous distribution. My question is, how do you know? Like, suppose you have a black box distribution and you're sampling trajectories from that. How do you know where is the discrete part and where is the continuous part?
So in this work, I mean, there's some results that I didn't show on actual like pedestrian data sets, like larger scale problems. There are some in the deep learning community, there's some methods that take the environment context, the map, the agents near the interactions, and come up with the Gaussian mixture model. So that Gaussian mixture model, you have a Gaussian along each mode, but you have multiple modes. So that's one way. There's also ways to do this where you have like some arbitrary distribution and you do a bunch of sampling and try to do as many samples as you can online to be as safe as you can. But in this case, we're using sort of learned Gaussian mixture models.
But when you're sampling, you suppose you're just sampling, all you get is a bunch of trajectories. From there is no notion of whether it's your discrete, what is the discrete part, what is the continuous part. All you have is a bunch of trajectories, and once you visualize this, obviously maybe you can identify, okay, this belongs to one cluster, this belongs to the other cluster. Yeah. But if you're sampling from, let's say, I have let's say a big neural network which is doing prediction, and all I can do is sample from that.
Yeah.
So it need not be even GML. So it can be like any arbitrary neural network which just gives samples. Then there is no continuous or discrete part there.
Yeah, so the way you can go about it in continuous or discrete sense then is you can capture the overlap between distributions. So like, let's say you're sampling, in our case, we have a GMM, and the way we actually pick our, what's it called? The robust horizon is we say, after which point, we put some threshold and say, after these distributions overlap by less than this amount, then they're distinct outcomes.
But do you need that? Like, if suppose there is a method which can just take discrete trajectories and give you the risk, no matter what the distribution are, without caring about discrete or continuous. My bottom line of the question is, why do you need this discrete and continuous quantification? Because first, you don't know. When you sample, you just don't know what is there. And secondly, if your method relies on this, having the discrete and continuous division, then it becomes a little bit tricky, because then
it doesn't rely on it. You can always, this parameterization, you can have it for a single sequence.
If you're doing GMF, then if you have modes, then your chance constraint is defined, let's say, for these modes. Then if you're leveraging the Gaussian properties of chance constraints to simplify the problem, then it may rely on.
Yeah, I guess the main advantage of, so if you have a method that would just give you a risk for a given distribution, you could of course do that. But the main advantage comes in where there are very different outcomes. And we're assuming we can know somehow that like at an intersection, you can kind of tell from the geometry of the intersection, the history of each agent and the interactions, what the outcomes will be and which ones will result in very different outcomes. But if you have a method of directly going from any arbitrary distribution to a risk value, then yeah. But this allows you to reason about different outcomes that result in significantly different behaviors for the robots. But you can always do something, a robust control method where you have some risk or some distribution that you're trying to avoid and just come up with a control sequence that satisfies.
I just want to give other.
But happy to chat after.
Yeah, I think this is a very interesting paper. So I think the nice part is we have lunch right after this. But we have time for one last question. We'll break it.
Thank you for the talk. And the first question I had is, if we want to restore conditions in the MPC, what are the time frames that you're using? Because I didn't mention that the time used to optimize the program is 90 minutes required which operate. If I think about the small error that robots might try to.
Yeah, so for those type of cases where you need kind of long-term reasoning, like whether you go down an aisle or a different aisle, that's not the scope of the local planner. So the way we envision this is you have something like CBS or a high-level global planner that's conflict aware, that kind of decides, okay, this robot goes down this aisle, that robot goes down a different aisle. And so we only care about local collisions for the next few seconds in this case. And the way we encode that is from the prediction of each MPC cell, we know we have an estimate of where the collision might be, assuming the robots follow their predicted trajectories. And then from that point of collision to the end of horizon is where we define our constraint set for each subsequent cell.
Question is then about the constraints. We want to use them in a real world application. Most of the tools I know with the robot. And did you have thought about adding the communication delays required to exchange them?
Yes, that's definitely on the list. It's not in this work, obviously, but one thing we have thought about is if you keep track of the last message received for each robot, you can come up with this sort of estimate of how much delay there is from the last time and expand your buffer for collision checking proportional to that delay. So the larger the delay, the more conservative you want to be with your collision checking. Of course, that can run into infeasibilities if the delay is longer, but it's better than not capturing delay at all. So
Thank you.
yeah, of course.
Thank you very much, Ardalan. Let's give him a big hand.
Thank you.